Keeper 2.2 Separable Differential Equations. All right, so this again is a review from last semester. Basically, what we do is we have a differential equation or something written in the form of dy dx. And what you want to do is just separate it so that your x's and your dx are on one side and your y's and dy are on the other side. And again, that's why we call it separable differential equations, because we can separate it to separate out the variables on each side of the equation. All right, so our first example, we have dy over dx equals e to the negative y times 2x minus 4, and they gave us an initial condition of y of 5 equals 0. All right, so the first thing I'm going to do is I'm going to separate this so that I get my y's on one side and my x's on the other side. If you notice, this e to the negative y is really just 1 over e to the y. So all I have to do is multiply both sides by e to the y to get e to the y dy, and then move my dx over to get 2x minus 4 dx. Once I get it separated out, I can simply integrate both sides. So the integral of e to the y is e to the y, and that equals the integral of 2x minus 4, which is x squared minus 4x plus c. Remember, you only have to add the c on one side. So in this case, we generally add it to our x side. All right, now once you have the plus c, once the immediate second you get that plus c, is always good form to go ahead and plug in your initial condition to eliminate any type of errors. So I'm going to plug in my initial condition where x is 5 and y is 0. And so then when I evaluate that, I get 1 equals 5 plus c, or c equals negative 4. All right, so then I'm going to take that c, I'm going to plug it back into my equation. So I get e to the y equals x squared minus 4x minus 4. Now to get y by itself, I'm going to ln both sides to get rid of the e. So I get y equals ln of x squared minus 4x minus 4. All right, so example 2, we have y prime equals 3x squared plus 4x minus 4 over 2y minus 4. Remember, y prime is the same thing as dy over dx. So what I'm going to do is I'm going to multiply both sides of the equation by 2y minus 4 and both sides by dx to separate my variables. So I'm left with 2y minus 4 dy equals 3x squared plus 4x minus 4 dx. Now that I have it separated, I'm going to go ahead and integrate both sides. The integral of the left will give me y squared minus 4y, and then the integral of the right will give me x cubed plus 2x squared minus 4x plus c. Now again, the second that we get that c, we plug in our initial condition. Our initial condition for this problem says that when x is 1, y is 3. So I'm plugging in 3 for y and 1 for x. When I evaluate that, I get negative 3 equals negative 1 plus c, or c equals negative 2. All right, so then I'm going to take that c, I'm going to plug it back into my equation to have a final equation of y squared minus 4y equals x cubed plus 2x squared minus 4x minus 2. Now, generally, we could leave this, especially like if it was an FRQ question or something like that, I could leave this as is, but there is a chance that you could get something like this as a multiple choice question, which might be solved for y. So if it's solved for y, you have to do a little bit more work. And the easiest way to extend on this is to simply complete the square. So if you remember completing the square, you take your b term, or the term in front of the y, you take that term, you divide it by 2, and then you square it. And whatever number you get, you add to both sides of the equation. So I'm going to take the negative 4 that's on the left-hand side of this equation. I'm going to divide it by 2, which will give me negative 2. And then I'm going to square it, which will give me 4. And so I'm going to add 4 to both sides of my equation to keep it balanced. All right, so by doing that, now I have on the left-hand side y squared minus 4y plus 4. That is a factorable expression, and I can factor that to be y minus 2 squared. On the right-hand side, I'm just simply going to add my like terms, so I get x cubed plus 2x squared minus 4x plus 2. All right, so now that I have that all factored out, I can square root both sides. Remember, my goal is to get y by itself, so I'm trying to get rid of the square by square rooting both sides. Don't forget that when you square root, you technically are left with a plus or minus. So I have y minus 2 equals plus or minus square root of the right-hand side. All right, my kind of last step is going to be to add 2 to both sides. So I get y equals 2 plus or minus square root of x cubed plus 2x squared minus 4x plus 2. And then my very, very last step, all I need to do is determine whether it should be plus or it should be minus. Remember, you can't have both, all right, because we had an initial condition. So I have to go back and check my initial condition. So what I'm going to do is I'm going to plug in 1 on the right hand side. Under the square root, when I plug in 1, I'm left with 1. So I have 2 plus or minus 1. But remember, I don't want the plus or minus, but I want the answer to be 3. So 2 plus 3 would give, or 2 plus 1 would give me 3. So my final answer should be the positive of the square root, or y equals 2 plus square root of x cubed plus 2x squared minus 4x plus 2. All right, so example 3 is more like a AP type question, or even like a question that I would put on the test, where I extend upon multiple concepts. So let's just work through a couple of examples of where I can use the same problem and ask you multiple different questions on that one problem, just like the AP exam would. All right, so part A for example 3 says consider the differential equation dy over dx equals y minus 1 over x squared, where x does not equal 0. It says on the axis provided, sketch a slope field for the given differential at the 9 points indicated. And so basically, again, all I do to get my slope field is I plug in the points into my differential equation. So like I plug in the point 1, 1, or I plug in the point 1, 2, and then I sketch a slope that resembles whatever number I get out. So like if I plug in the point negative 1, 1, I would get 0 out because I have 1 minus 1 on top, and then negative 1 squared is 1, so I get 0 over 1, which is 0. So I'm drawing a horizontal line to indicate a slope of 0. If I do the same thing for 1, 1, I get 0, and I'm also going to get the same thing for 2, 1, because all of those have a y value of 1, which is going to leave me 0 in my numerator. All right, so next one I'm going to do is negative 1, 0. If I plug that in, or sorry, yes, negative 1, 0. If I plug that in, I'm going to get negative 1 over 1, which is negative 1. So I drew a slope of negative 1. I'm going to do the same thing for 1, 0, which is going to give me a slope of negative 1. And then if I do it for 2, 0, I'm going to get a slope of negative 1/4. And so I drew a less steep line for that. And then I do the same thing for the top. And this is the graph that I come up with. All right, now again, our graphs might not look exactly alike, but you just kind of want to make sure you're trying to get your lines to look like the slope that you found. All right, so part B, we have the same differential equation, dy over dx equals y minus 1 over x squared. And this time they want us to find a particular solution with the initial condition of 2, 0. So first I'm going to separate this out to try to solve this out for y. So when I separate it, I get 1 over y minus 1 dy equals 1 over x squared dx. I'm going to integrate both sides to get ln of absolute value of y minus 1 equals negative 1 over x plus c. Again, since I just got my c, I'm going to go ahead and plug in my initial condition. All right, so I get ln of 0 minus 1 equals negative 1/2 plus c. Since the left-hand side is absolute value, that's still the same thing as ln of 1, which is 0. And then I'll solve that out a little bit more to get c equals 1/2. So plugging that back into my equation, I get ln of absolute value of y minus 1 equals negative 1 over x plus 1/2. I'm going to e both sides. Then I'm going to get rid of my absolute value by placing the plus and minus in front. And then I'm going to add my 1. Now remember, we can't have plus or minus since we have an initial condition. We have to figure out which one we want. So if we go back and kind of mentally plug in our initial condition, if I plug in 2 into the right-hand side, I get e to the 0, which is 1. And I want the answer to come out to be 0, so I want it to be 1 minus 1 instead of 1 plus 1. And so I know that I need to go with the negative of the plus or minus. And so my final equation is y equals 1 minus e to the negative 1 over x plus 1/2. All right, so then part C says, well, consider that same differential equation, but this time I want you to take your answer that you got in part B and find the limit of that answer. So remember, our answer from part B was 1 minus e to the negative 1 over x plus 1/2. We're doing the limit of that answer, so I'm plugging in the limit as x goes to infinity. And so I get 1 minus e to the negative 1 over infinity plus 1/2. Well, 1 over infinity is 0. So I get 1 minus e to the 0 plus a half, or 1 minus e to a half.